Okay, today is our second session of the mini course. The title, you know, like, an introduction
is the same as yes.
But I can repeat. Introduction to Proof Assistance, a mini course about mathematical formalization. The professor is Riccardo Brasca from the Université Paris-Cite. So please, you can today follow this beautiful course.
Thank you, Daniel. So, thank you for coming also today. I slightly changed my plan. So instead of watching me doing a simple proof, I think it's probably more interesting to, first of all, have a look at the library. So yesterday I mentioned several times MATLib, but we didn't really have a look of what MATLib is. So as I said, is in Lean mathematical official mathematical library. So the idea is very simple. When you do some mathematics, if you have to prove a theorem, of course you use a lot of theorems proved by someone else, and so you don't want to start from scratch every time you have to prove a new theorem. And of course in MATLib we do the same, meaning that if someone had proved the very simple results we saw yesterday, people can use them to prove things much more complicated. So we will try to have a look at the library to see how far we went in formalizing mathematics and what is still missing. So first of all, let me say some words about MATLib. So it is a large monolithic library. So what does monolithic mean? It means that it is essentially one library. All the results are compatible among themselves. Everything is connected. So if MATLib knows, for example, real analysis, abstract algebra, but the definition of the real numbers in MATLib is compatible with the definition of groups, of a group in MATLib. So this is interesting because it's something that is quite rare to find in formalized mathematics. For example, other proof assistants have big library, but sometimes they are not completely compatible. So maybe you have the library, the analysis library, and the algebra library, and they don't speak. They don't speak. And so, if you want to say that, I mean, this is possible. But if you want to say something like the real numbers have this algebraic property, sometimes it's complicated because the analysis part doesn't really speak with the algebra part. In MATLib, we really try to build just one library. This is, of course, it's better, and it's mathematically what we want to do, but it's much more work. So this is why other proof assistants don't do this, because they just prove the result they need to get to some specific result. In any case, the goal of MATLib is to be used by standard mathematicians, meaning by mathematicians that work in mathematics department. So the focus of MATLib is really to try to write formalizing mathematics as similar as possible to write mathematics at the blackboard. For example, it is about classical mathematics. So this word classical is a technical term, so it doesn't mean standard. Classical mathematics means that we use the excluded middle. So excluded middle is the sentence that if something is not false, then it is true. So this is something that your professors use all the time in proofs. For example, they use this in doing proof by contradiction. If a proof starts saying, let us suppose that the conclusion is false, then blah, 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 we arrive to something absurd, so our hypothesis must be false, and so the theorem is true. This is a pattern proof that uses excluded middle, and in MATLib we use it all the time. I mean, not all the time, but we can use it without any problem. Other proof assistants are more interested in try to avoid the excluded middle if possible. So I don't want to explain why they do that, but because they are interested in something that is slightly different, but it is an interesting stuff to do, to avoid this excluded middle. But in MATLib, we try to focus about classical mathematics. For example, it uses the axiom of choice everywhere. So I mean, I don't want to explain what the axiom of choice is if you don't know it, but if you know what it is, it's something that is really used in mathematics more or less all the time. I mean, if you want to do real analysis, you need some form of the axiom of choice, at least countable choice. And of course, I mean, the point is that if one has the axiom of choice, then it can deduce excluded middle. So the real thing is that in MATLAB, we have the full axiom of choice, and then excluded middle is a consequence of the axiom of choice. So in any case, what I'm trying to say is that we really try to have a library that is as similar as possible to what a mathematician does. So let's have a look at some statistics. So there are more than 42,000 definitions in MATLAB. Not all of them are interesting. There are a lot of trivial definitions, but there are also interesting definitions. There are more than 100,000 theorems. Again, not all of these theorems are difficult or interesting, but there are difficult theorems. And it has, as today, we had 280 contributors. So anyone can contribute to the library, and there are 280 people that contributed to the library. So MATLAB knows a lot of undergraduate mathematics. We will see in a minute an overview of what MATLAB knows, and also some graduate level mathematics. For example, we will see that it's quite strong in algebra and number theory. It's a little bit less strong in differential equations, but we are getting there. And maybe it's not really strong in probability, but this is just because people didn't start formalizing probability, but I'm sure it will happen soon. So let's have a look let's see an overview of the library. So this is maybe I can just increase the font. Yeah, okay. So you see, this is a list of results that are already formalized in MATLAB. So maybe something you are more familiar to, it's, I don't know, for example, about linear algebra. So you see that, MATLAB uses this fancy name, if you don't know what it is, module. Just read vector space every time you see module. For the expert, there are no vector spaces in MATLAB. It's because, of course, we only have modules over field. So. But yeah, it's not very pedagogical to read MATLAB code because it's written by experts. So we don't need vector spaces. We just speak about modules and so on. But you see, he knows, for example, what the matrix associated to a linear map is. I don't know, the change of basis formula, stuff like that. What eigenvalues, eigenvector are, and so on. So you see that he knows quite some topology. He knows some analysis. He knows about Banach spaces, Hilbert spaces. He knows about integration. Of course, he doesn't know about Lebesgue integration because Lebesgue integration is not general enough. We only have the Bochner integral, that is a generalization of the, he has the Lebesgue measure, but he doesn't have Lebesgue integration because we had a more general version that's called Bochner integral. But still, I mean, we have LP spaces and so on. We know a little bit about.
I'm teaching functional analysis.
Yeah.
So you have adjoint.
We have the adjoint of an operator on a Hilbert space. We don't have the spectral theorem yet. We have the spectral theorem. I mean, we have some special case of the spectral theorem, but not the full one. But yes, the adjoint of an operator we have. Then. There are some probability theory. Okay, so this should be pretty new. Then we have some geometry, combinatorics, and so on. I mean, I don't want to.
This list is every day changing, or
no,
every week?
This list is maintained by human beings. So if you add something that is not on this list is surely not complete because maybe someone added a theorem but forgot to add it to this list. So this is done by human beings. And if you add a new theorem, you are supposed to put it here if it's an important one, or someone is supposed to tell you to put it here, but sometimes we forgot. So, now, if you want to look at the real one done by a computer, and this change every day. So, for example, let's take I don't know, something that will be probably readable. Yes, no, something about The Euclidean division for polynomials. So if you have two polynomials, you can, we have an algorithm you have a theorem that says that you can divide the polynomial and the remainder as degree is smaller than the one you are dividing. If I click here, I go to, this is done by computer, and it changes every day, these pages. I mean, every day, every time someone changes the pages. So you see, we have, this is the theorem that, you see, this is pretty readable. You have R, a set, as I said yesterday, when you say type, read a set, that is a field. Then the ring of polynomial over R is a Euclidean domain. So if you don't know what Euclidean domain means, it's not important. The important part is that you can divide by, you can take divisions. And you see, so the proof is hidden. You have to click on the source code to see the proof. It will be difficult to read, I guess, yes. So this is the proof, but I mean, we don't care. And then we have a long list of trivial theorems about this stuff. For example, I don't know, the fact that, let's have a look at this one. So polynomial dot degree div underscore LT. Okay, I understand that the name looks like very weird, but it's, you see LT, it means less than. And so it says that now you take P and Q polynomial over R. That is a field again. You suppose that P is different from 0. That the degree of Q is bigger than 0. Then the degree of P divided by Q is smaller than the degree of P. So this divided by is the quotient in the Euclidean sense. So of course, we are not requiring, there is also a reminder, but I mean, this is the quotient in the Euclidean sense. So, and you see that now we have a long list of theorems like that. So we have more than 100,000 theorems. So for example, if you want to see more reasonable, so here is the list of really everything that is in MATLib. For example, let's have a look at the number theory folder, because I mean, I know it. So you see, for example, we have results about the cyclotomic fields, if you know what it is. I mean, I'm showing this because I wrote essentially all this folder. So for example, this is a file. If I click here, I see the list of theorems proven in this file. So there is a small abstract about what is proven in this file. So the idea is that we got the results about cyclotomic extension of Q. In particular, we compute the ring of integers of a P to the n cyclotomic extension of Q. Again, if you don't understand the mathematics, don't worry, it's not important. It's just to show you something. And then there are the theorems. And somewhere here, it's probably, yes, for example, it's this one. That's if you take, so the ring of integer of a p-th cyclotomic extension of Q is what it is. So it's the subring generated by a primitive root of unity. So just to give you an idea, this is a first-year graduate. I mean, this is a theorem that is taught in a first-year graduate course in number theory. I mean, that can be taught in a first-year graduate course in number theory. It's not very difficult, but it's not easy either. And if you want to see the proof, you can just click here. Okay, so here this proof is very short because this is probably just a special case of a previous theorem. But you see that the proof of this one is slightly more complicated. I mean, is longer. And so you see, the proof is, of course, much more complicated than what we saw yesterday, but you see that the structure is the same. We have several tactics. For example, here you can recognize the exact tactic that we saw yesterday. Oh, sorry. We also saw the obtain tactic. And there are other tactics like convert or simp. I mean, I don't want to explain this one because it's complicated proof. But we have a full library like this with more than 100,000 theorems. So let's have a look now at how the library grows. So now he has more than 1 million lines of code. And here is a graph about the number of lines in MATLib. So you see that here we started quite, so MATLib started in 2017. At the beginning, the growth was pretty slow, but here, there have been an acceleration here, maybe because of lockdowns, I don't know. Yeah, I mean, I guess so. So now the growth has always been linear, but now it's linear, but not with the same coefficient. So now it's better. And okay, yes, now we have more than 1 million lines of code. And this is the number of commits by month. What is a commit? Essentially, a commit is a contribution to MATLib. So every time someone wants to change MATLib, has to submit propose the change to a committee of people, and we review this change, and when we accepted it, it becomes a commit. So it means that, for example, in September 2022, this year, we had a little less than 400, so I don't know if this is, no, this should be August. So in September, we had more than 400 changes to MATLib. Of course, not all of these changes are interesting. Most of them are pretty small and maybe even trivial. We saw yesterday someone just fixing a typo in the documentation, so this is perfectly fine, of course. So every month we have around 400, maybe 400 or 500 contributions, sometimes trivial contributions, but sometimes interesting ones.
Riccardo, one question. So maybe you are going to say that after, but if someone here in the public or someone on Zoom is motivated to contribute here, it is possible in some reasonable...
It's totally possible. It's totally possible. I'm going to explain this, but yes. Let me, so MATLib is an open source project, and we accept contribution by anyone. I wouldn't suggest doing immediately contribution to MATLib because we have quite high standard of quality. So at the beginning, it's, I mean, learning how to code in Lean and learning how to code following MATLib styles are two different things. Of course, the hardest part is learning Lean, but there is also the part of learning our convention and stuff like that. So what I suggest is just to start coding, even maybe with code that has not a very high quality. And when someone has a good contribution, they can try to contribute to MATLib. But it's really open to anyone. I mean, this is what I started 2 years ago working on Lean. And I think that I started in September, and I opened my first PR. So I mean, I submitted. I tried to contribute to MATLib 2 months late, maybe one month and a half later, something like that. So at the beginning, it's really better to focus on just learning Lean before trying to contribute to MATLib.
But you don't need to be a professor to do it.
No. Anyone can do it. No. We have contribution by students all the time. All the time. Yes. You have to learn Lean to learn how to code in Lean, of course. But no. Anyone can contribute. So just to show you, let's see what happened in MATLib in September. So this is a list of the most interesting contribution to MATLib that happened in September. So we saw that we had more than 400, I don't remember. Not all of them were interesting, but you see that we have some interesting contribution. For example, I don't know, in analysis, we now have a Stirling formula. So this should be nice. So Stirling formula is an approximation of n factorial using the exponential. And so if I click here, I should see the pull request with the proof of Stirling formula. Yes. Oh. Okay. It's not very readable, but this is probably Stirling formula or something like that. I don't know. Yeah, it's much less readable than I thought. But in any case, so it's a pretty famous result in analysis that since September is in MATLib. And you see we had some probability theory, combinatorics, something in number theory, and stuff like that. And this happened every month, essentially. So this is a pretty standard month in MATLib. Okay. Oh, so this is the same graph but by year. So at the beginning, the library was not very active, but now I mean, every year it's better and better. And I'm sure that, I mean, maybe we will get to 5,000 commits this year. I don't know. We will see. Exactly. As I said, anyone can contribute to the library. So, and even better, to any part of the library. So at the moment, we have more than 500 open pull requests. So a pull request is someone saying, oh, I did this. Can you please include it in the library? I mean, I also have two or three pull requests open in the library. Because, I mean, of course, I can technically accept my own pull request, but this is not what we do. So even among us, we try to review our pull requests. And there are really 120 that are marked awaiting review, meaning that there are people actively working on them. So there are people that are really waiting for me or my colleagues' answers. And I mean, we try to be as fast as possible, but sometimes we have a lot of stuff to do. And we accept pull requests about anything in the library, for example, all areas of mathematics, but also if you want to improve the tactics that we saw yesterday, you can even try to really change the core library, so to really change Lean itself. This is, of course, much more complicated, and I'm not an expert in this. You can, I don't know, contribute to the editor's extension if you know how to do. I mean, you can really contribute to anything. But, I mean, the important thing is that really we accept contribution by anyone. Anyone is really welcome to contribute. If you are interested in really joining the community, what you have to do is to, I mean, the entry point of the community is a chat that is on Zulip. So Zulip is like some sort of social network. Yeah, you can click here, and you can go to the Zulip chat. I can show you how it looks. So you see, this is a place where all the people working on Lean interact. And so you see that there is a stream called the new members, where even if you are a total beginner, you can ask any question. So there are no stupid questions. We all started here asking questions that are now, I mean, now we think they are completely trivial, but when you are a beginner, they are not. So you see, you can just register and saying, okay, I mean, I would like to learn Lean. What can I do? Well, does someone has a small project for beginners and so on? The community is really, really very nice, and there are no stupid questions. Anyone can ask any question. Just be sure to post it in the new members stream that is done. I mean, it exists exactly for these reasons. But feel free also to have a look at other stream. For example, I don't know, you can see here a discussion about something in graph theory. So I don't want to read it. We have a stream for dedicated to mathematical questions. So here someone is saying that is doing something about elliptic curves. So yesterday we had this question, what is the situation about elliptic curves? I don't know what is the situation. So I think they are still discussing, I mean, I'm pretty sure we are still discussing, yes, how to prove associativity in characteristic 2. So maybe he did it? Associativity is still in progress. Okay. No. Okay. So you see, I mean, there is really an active discussion about what we're doing with Matlib. So feel free really to join this chat if you are interested, and to ask any question. All questions are welcome, and the community is really nice. So don't be shy. Don't be afraid of asking questions and to register. So let me explain now. So this was my short presentation for today. What I'm going to do now is to show you some code as yesterday, but with already in mind what we are going to do next week. So I slightly changed my plan for my new plan for next week is to let you play a video game based on Lean, of course, that is called the natural number game. So you can just Google the natural number game, And you don't need to install anything. You can really play it online. So you see, this is the video game. So what is the point of the video game? The video game knows what the natural numbers are, but it doesn't know any theorem about the natural numbers. For example, it doesn't know that, I don't know, the addition is commutative. So the goal of the video game is to prove theorems about natural numbers. And it's very simple to use. This is why I think it's the best you can do next week. So with avoiding all the problems in installing stuff and similar things, you just click here. You see, so this is the first word, the tutorial word. Of course, the tutorial word is very easy. You have to wait a little bit. You see, after you clicked, it says Lynn is busy, but now he's ready. And then you have your first proof. So, and we are not going to read this now, but at the end of today's lectures, I'm going to solve the first 2 or 3 levels just to show you how it works. But you see that it's very similar to the editor I showed yesterday. It's not exactly the same, but essentially it is the same. So you have to write the proof between begin and end, and here you can see Lynn's mind. Okay? And you see that there are several levels. So the first one is very easy, but at some point the proofs are not so trivial. At the end of the game, one can prove that natural numbers are something like a commutative, ordered semi-ring with exponentiation, something like that. So that you can add natural numbers, multiply natural numbers with the usual rules like associativity, commutativity, distributivity, and so on. That you also have a notion of order on the natural numbers, so you know what A is smaller than B is, and that the operations are compatible with this order. So if A is smaller than B, and C is smaller than C, and C is smaller than D, then A plus C is smaller than B plus D, or whatever. So you have to prove all this theorem. Okay, so let me, sorry. Stop doing that, okay. So before even starting playing the game, I think it's interesting to see, okay, but even before proving any theorem about natural numbers, one very basic question is, what is a natural number? I mean, we are trying to formalize mathematics, so we are trying to be as precise as possible. So, I mean, Lynn is completely stupid. The computer is completely stupid, so someone has to tell Lynn what a natural number is. So what I'm showing you is now the definition of natural number, and I'm trying to explain what this definition means. So ignore this line. It's just to use some tactic, but this is not important for you. This is the definition of natural number. So I'm defining a new type that I'm calling my nat, just to show you. So I don't want to show you. I mean, just to show you that I'm not cheating. Ah, sorry. Yes, I forgot the most interesting part of the talk, the video. So sorry. Before doing this, you see that in the library we have a lot of theorems, but also a lot of files. Now, for example, in this number theory folder, there are a lot of files that are really interconnected among themselves, because maybe one file uses 30 files that have already been written. And so what we can do with such a structure, of course, is making a graph. So this is the graph of all the files in MATLib. So, and each line lines mean that okay, there are really a lot of them, but maybe I should stop it. So this file, algebra.order.group.basic, uses it's imported by algebra.order.ring or whatever. So you see that we really have a lot of them. I think that there are more than I don't know, maybe 30,000 files or something like that, but I don't know. And what I can show you is a small animation of how people contribute to these files, So, okay, so this is a short. So this is a video. You see there is a date here. So we are in August 2017. Now each dot is a file, okay, and each small pawn is a mathematician, is a contributor to MATLAB. So you see that they are going around, and when there is a ray like that, it means that this person, you can even know who the person is. So, okay, you have to. Okay, so this is Gabriel Ebner. Okay, so, and they are contributing to some files. So you see that in October 2017 there were not so many files. Now every second is 2 days. Sorry, and these are all the contributions. Again, are all the contributions made to MATLAB by all the people. So you see that this is not so very, it doesn't look very, very active, but because we are very at the beginning of the library, if I skip to, for example, 2000 and yeah, so this is so here we are in, maybe let's go to, okay, this is January 2020. You see that is already much more active with much more files. And sometimes, so remember that each row means that this person made a modification to these files, and sometimes you see big flashes when some power users modifies at once a lot of files. You see, like that one. So this means that someone, I mean, I can check which contribution was, but I don't want to do that. So that person modified a lot of files at once, because maybe he made such a fundamental modification to the library that he had to modify a lot of libraries. Look at it in another one. And so maybe we are not going to see all the full video, but let's go to, so this is much more recent. So this is June 2022. You see that now the files are, we have really much more files and much more contributions. And I mean, there is the pawn corresponding to myself somewhere. I don't want to find it, but you see, you can see the name, and you can also see the name of the files if you want. But okay, so this of course this video is just to, I mean, it doesn't make any real mathematical sense, but it's just to show you that we are really an active community. So we really modify the library a lot. And we are not afraid of big modifications. So these big flashes where some expert modify a lot of files at the same time. Okay. So let me just show you the actual definition of natural number in MATLAB. So you will see that is exactly the same as I wrote in my example. So you see, you keep in mind this definition, but I can assure you is literally, I did the copy paste, so it is exactly the same as here. So here I'm defining a new type, and I want to define natural numbers. So I define a new type that I call my_nat. So this will be my natural numbers. That is a type. So read, it is a set. Then there is this keyword inductive, forgot about it. And then there are these two pretty mysterious lines. What do these two lines mean? So the first line, it means that there is a natural number that I call 0. So this is some sort of an axiom. I say that there is a natural number called 0. And the second line says that every time you have a natural number n, you have another natural number that will be called the successor of n. Okay, so maybe I have to write down the password, sorry. Nah, now, sure. Okay. Okay, so technically what we say is that we have two constructors for natural numbers. So we have two ways of creating a natural numbers. The first way is just saying that you can take 0. I mean, if you need a natural number, you can take 0. And the second way is that if you already have a natural number, you can create another one called the successor of this of natural number. So technically, the successor will be a function from my nat to my nat. But the idea is that there are two ways of building natural numbers. One way is just taking 0. This doesn't require anything. And the other way is to consider the successor of natural number. Now, there is this line that is just to use this beautiful symbol, but mathematically doesn't mean anything. Now, there is this line that it just means that I will not have to write my nat dot 0. I can just write 0 to tell Lin this 0 is the 0 of my nat. Now, these two lines are not very important. Essentially, you see, here 0 is called 0. But we want to use the symbol 0 on our blackboard. And so these lines allows me to write really the symbol 0 as here. And Lin understand that it is a my nat. And similar, here I'm introducing what is called 1. So you see that I'm saying that my natural numbers have another special element that it's called 1, and I can access to him using the 1, writing 1 with my keyboard. That is, by definition, the successor of 0. So 0 is a natural number because this is one of our axioms. And then we can take the successor of anything, of any natural numbers. In particular, we have the successor of 0. And I just decide to call these natural numbers, to call it 1. So 1 is, by definition, the successor of 0. OK. What is doing Lin when I say inductive my nat, blah, 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 is also creating a new axioms. These new axioms essentially is saying that, OK, we have these two ways of introducing a natural number, and that's it. So that there are no other natural numbers. So that any natural numbers is the successor of the successor of the successor, blah, 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 of 0. So these are the only way of creating natural numbers, taking 0 and taking the successor of the successor of the successor, and so on. OK? Lin has a pretty complicated way of stating this axiom, that there are no other natural numbers. But the interesting part, so I'm not showing you the actual axiom he's creating, that is called mynat.rec. But a consequence of this new axiom is that essentially we have, for example, the induction principle. So this is automatically introduced by Lin. If you want to think that this is introduced this is a new axiom about natural numbers, but in reality the real axiom is slightly different. So this mynat.inductor is the principle of mathematical induction. So let's have a look of how Lin states this in mathematical induction. So we take phi, a function from n to propositions. So essentially phi associates to any natural number a proposition. For example, phi can be phi of n is even. You see, this is a proposition. Sometimes it's true, sometimes it's false. It depends on n. But it is a proposition defined for any natural number n. OK? So think about phi as a proposition defined for any natural number n. So what does the induction principle say? That if we want to prove a proposition about any natural number, we need to prove it for 0. And then we need to prove that if the proposition is true for n, then it's true for the successor of n. And you see, this is exactly what we say here. So we have this, our proposition phi. We say that phi of 0 implies that phi of n implies phi of successor of n implies phi of n for every n. So in practice, what is written here is that if we have phi of 0, and we have that for all n, phi of n implies phi of the successor of n, then we have phi of n for all n. So this is exactly what is usually called the principle of mathematical induction. Okay? So you see that Lean almost introduced this principle as a new axioms. But the idea is really that what Lean is trying to say is that there are no other natural numbers rather than 0 and the successor of something. Here I'm proving this theorem using the real axiom Lean introduced. That is more complicated that I don't want to show you, but you see that the proof is very short because this is very, very close to the principle of mathematical induction. But what Lean adds is slightly more interesting than the principle of mathematical induction. So we see that now we have a way of introducing natural numbers. I mean, two ways, 0 or the successor of something. Now we have a way of proving stuff about natural numbers using the mathematical induction. But how can we define a function out of natural numbers? So how we can build a function from n to s, where s is some set. We can do it by recursion. So when we speak, we distinguish induction and recursion, but under the hood for Lean, these are exactly the same thing. So Lean creates also almost create a new axioms that allows us to define function out of n by recursion. So it says the following thing, that let's suppose that we want to build a function from n to s, where s is some type, some set. We have to say, what we have to do? We have to say where 0 goes, okay? And then we have to say where the successor of n goes if we know where n goes. Now, in this way, if you want to say, you know where 0 goes, now you know where the successor of 0 goes. So you know where 1 goes, then you know where the successor of 0 goes, etc., etc. And since there are no other natural numbers, you know where any natural number goes. And you see, this is expressed in the following way in Lean. So for all s type, we need to, if we have an element of s, that will be the image of 0, and for all natural number n and all element of s, we need another element of s. Think at this line in the following way. For all n, if we know the image of n, we need to know the image of the successor of n. So given n and s, this s morally is the image of n. And the element we need to choose is the image of the successor of n. Then this function will build for us the full function from n to s. So I know this is slightly more complicated, so let me say it again. To build a function from n to s, we have to do two things. First of all, choose the image of 0. It is this line. This is clear. Second thing we have to do is to decide where the successor of something goes. But you see that it's much better to do it step by step. So when you have to decide, you don't have to decide where 3 goes if you don't know where 2 goes, because you know where 0 goes. So now say where does 1 go? But you can use that maybe you know where 0 goes. You can also ignore this information if you want. But so the idea is that you have to specify where the successor of n goes, knowing where the successor of n goes. If you can ignore this information if you want, but you can also use it if you want. And you see that the proof, again, is difficult to read. It doesn't matter. But you see that I'm using the same theorem as before. So what really Lean is doing when I define natural numbers is declaring only one axiom, that is this one, that you see it's not very beautiful to read, that essentially it encapsulates the principle of mathematical inductions and also the construction of functions by recursion. So for Lean, these two are special cases of the same more general construction that we don't want to know. So let me give you an example. For example, let's suppose that we choose natural number a, and we want to define the function that sends n to a plus n. So I'm defining the function that sends n to a plus n. And how I define it, I'm using I'm defining it by recursion. So what I have to specify two things: where 0 goes, and of course I did a mistake. It goes to a. Okay. Now it's better. So where 0 goes, I mean, we want that a plus 0 will be to be equal to a. So the first thing here I say I'm specifying a function to n, and 0 will be sent to a, and then if I know where now we know the image of 0. Now take any natural number n. I have to specify the image of n. So what a plus n is. Sorry, not the image of n. The image of the successor of n. So I have to specify what a plus the successor of n is. But let's call x the image of n. So x is, if you want, a plus n. But it's just a name for the image of n under this image. So the image of a plus the successor of n will be the successor of a plus n. So if I call x the image of a, the image of the the image of n, sorry, the image of the successor of n will be the successor of x. And this is indeed the definition of the addition. I mean, of the addition function. And this is it's not exactly written like that in the library, but it is essentially like that, because in the library it's written directly with the two variables. But so now I defined addition a plus something, and of course I want to have access to the function of the two variables. But let's just ignore it. Okay, so the goal from the rest of my lecture is to prove this very interesting theorem, that 0 is different from 1. Okay, so you see that I've never said that the successor. So remember that 1 by definition is the successor of 0. And I never said that the successor is injective. So Lin is not supposing it. The only thing Lin is supposing is essentially these two theorems: the principle of mathematical induction and the fact that we can construct functions by recursion. So we are not supposing that the successor is injective. It's true, but we are not supposing it. But even before digging into the question how to prove it, there is one more basic question. Does someone see the basic question here? What does not equal mean? No, but I mean, it's tricky. It's a tricky question, but because you think that you know what not equal means, but now I am asking you the question. Since you didn't ask me, what does not equal mean? You cannot say not equal is not equal. This is circular, no?
So the question is, what?
I mean, here there is a symbol. This symbol here. I mean, there are 3 symbols in our goal.
Yes.
Okay, the first one is 0. This is introduced by an axiom that says that we have 2 ways for introducing natural numbers. One of these 2 ways is just saying 0 is a natural number. Then the last symbol is 1. This is by definition the successor of 0, where the successor is our second way of introducing natural numbers. But there is 1/3 symbol.
Maybe someone on Zoom or here want to answer. Oh, Marco.
Voy a tratar de decir en inglés. We can define the not equal symbol like when the two numbers have not the same antecessor?
I don't know what an antecessor is.
The inverse of the successor function?
No, yes. Yes?
There's a proposition which satisfies one and not the other, something like that.
Okay, you
There's
can try
different
to do
answers.
something like that, yes.
Maybe,
but indeed, I mean, there is a more fundamental stuff that anytime you have a proposition, you want to be able to speak about the negation of this proposition. So this must exist. In mathematics, we do this all the time. So it must be in Lean somehow. And this has a definition, of course, in Lean. So if you have a proposition P, so let's suppose that you
are answering the question, or
yes, I'm answering the question.
It's not still open the question. Okay.
No. I mean, you can try if you want, but no. It was the real question was just I wasn't expecting an answer because I mean, if you don't know it, it's essentially impossible to guess the answer. The interesting part is that there was a question. So the interesting part about the question is not the answer, but is that, I mean, the answer is reasonably interesting, but is that the question, even the question exists, the existence of the questions. So let's suppose that we have a proposition P. Oh, sorry. I can ask Lynn to check, so what P is a proposition, very good, but I can also ask Lynn to check what not P is, and you see that Lynn says, okay, not P is a proposition. Very good, so he knows this symbol. So I can dig into the notation to see exactly how this is defined, but the definition is that not P is by definition, P implies false. Okay, so if you have a proposition P, the negation of the proposition P is an implication. Which one? The fact that P implies false. So here, in our proof, even if it's written like that, so this is, by definition, is not equal. It's just a fancy symbol to say it's not 0 equal 1. I can say change not 0 equal 1. It should work, yeah. Yeah, okay. So now, so this was just a notation to make it more readable. But so this is now an implication. It means that 0 equal 1 implies false. How do we prove an implication? If I ask you to prove that something implies something else, the first move to do is to suppose something, no? If you want to prove that P implies Q, the first thing you do is you say, let's suppose P. So here we start by saying intro H. So you see that now we know that 0 is equal to 1, and we have to prove false.
Can I ask you some
Yes.
questions? So the statement 0 different of 1 is a proposition?
Sure.
Okay.
It looks like a proposition, no? It's a mathematical statement.
Yes.
Okay, now if you are picky, you can maybe keep on asking questions because now we have 4 symbols in our here. So 0 and 1 are okay, but now okay, before we had not equal, now we have equal. So we can maybe even ask what equal means. I'm not going to answer, but there is a definition of equality in Lean. This gets slightly complicated, so and it's very low level, and I don't want to enter into this.
Sorry, I'm just confused. Weren't you in the process of answering the question?
No,
what
the answer,
equality means?
The question what 0 different from 1 means, the answer is it means 0 equal 1 implies false.
Yeah, but on top of that, you said, what does it even mean to be equal, right?
Yeah. This is a new question, if you want.
Okay, but you're not answering.
No,
that
I
now.
don't want to answer this one because it's too fundamental. I mean, but just to say that, of course, I mean, 5 minutes ago I said there are 3 symbols let's try to define them. Okay, now there are 4 symbols, so it's even more complicated. But Lin has a definition of equality. I don't want to answer. But there is another symbol that is false. So what is false? We can click on false and say, go to definition. So you see that false is exactly is a type like natural numbers and here in this line there is the list of way you can introduce something of type false. You remember that a proof of false is something of type false. And you see that there are no way of introducing something of type false. Because, I mean, we don't want to be able to prove false. So by definition, false is the type such that we don't have any way to introduce elements of that type. Okay. So now we are at our we are ready to start the interesting part. So we suppose that 0 is equal to 1, and we need to prove false. So here is the strategy of the proof. Essentially, we are going to define using the construction by recursion. We can define it. Let's suppose that there is a type with 2 elements, 2 elements that we call A and B. And let's suppose that we know somehow that these 2 elements are different. We can now using this function, we can define a function from n to this type in the following way. We send 0 to A and the successor of anything to B. Okay? Let's suppose that we know that A is different from B. Now, we know that 0 is equal to 1, so f of 0 must be equal to f of 1. But f of 0 is A, f of 1 is B, and we know that A is different from B. So we got to, it's not technically true, but let me say that we got to a contradiction. So this is the idea of the proof. If we are able to access to, we will write the proof, don't worry, but what I'm saying is that we need any set with 2 elements. We don't care about natural numbers, real numbers, or whatever. We need to prove the existence of a set with 2 elements. And so this is what I'm going to do in the next 5 minutes, and then we will go back to this proof. So let's do something simpler. So instead of proving that 0 is different from 1 in the natural numbers, let's just build any type with 2 different elements. But we are going to prove that the 2 elements are different. So let's keep this example with the sorry proof. And let's introduce a new type that I'm calling my type. So you see that the syntax is similar to the definition of natural numbers. There are 2 ways of introducing elements of my type. For natural numbers, the 2 ways were really different. Now, one way was just saying 0 is a natural number, and the other one was taking the successor of a natural number. Here, the 2 ways are similar and very different, and very, very simple. So I'm saying that there are 2 elements of type my type, A and B. As before I was saying 0 is a natural number, now I'm saying A belongs to my type, and B also belongs to my type. I'm not forcing A to be different from B. I'm just saying, create this. There are 2 ways of introducing elements of type my type. One is saying use A, the other one is saying use B. So it's like natural numbers, but the second way is much simpler. Okay? Now, exactly as for natural numbers, Lin is creating 2 new axioms related to my type. So something that we can call the principle of mathematical induction for my type. So how can we prove a proposition for all the elements of my type? But now it becomes really stupid, because you see that if we take phi, a proposition relative to any element of my type, if we know it for A and we know it for B, then we know it for all elements. Okay? this is now completely trivial, but I mean, this is Lean's way of saying that there are no other elements of type my type. Okay? So if you want to prove a proposition for all the elements of my type, well, you can prove it for A and prove it for B. And you see, this is really parallel to what we did for natural numbers. The difference is that the second constructor for natural numbers was much more complicated. So the principle of mathematical induction was more complicated. Here is very simple because the second constructor is like the first one. And again, how can we build a function from my type to any set S? Well, we have to choose where A goes and where B goes. Now this is totally trivial, okay? So again, this is parallel to what we did before. The only difference is that it's much simpler. So now what we are going to do is to prove that A is different from B. And really, we are really proving it. To prove it, we need first of all to introduce another function that goes from my type to prop. So this is essentially a function that take two elements of type my type, and it says that if they are true or not. But I'm defining it by hand. So you see that Lean is smart enough to support this nice syntax here, but in practice this is defined using these almost axioms here. But essentially, I'm saying I define my type equal AA is true, AB is false, BA is false, and BB is true. So I'm defining it that way. So this is my definition of the function. You can also ask what we saw what false is, what true is, but you see that true is another proposition that we have a way of producing a proof of true out of nothing. What we need to prove something that is true? Nothing is true. So essentially, true is the proposition we are able to prove without doing anything. Okay, now we are almost done. Don't worry. Now we are going to prove the following theorem. That I don't care about the name. I'm using later. So we take two elements of type my type, S and T. Okay, you see? We suppose that S is equal to T, and we are going to prove that my type equal ST is true. Remember that by definition, my type equal ST is a proposition. So it can be true or false. And I'm saying that if I know that S and T are equal, then this proposition is true. So mathematically, there is strictly nothing to do because we can say, I mean, it's defined by 4 cases. Just check that this is, we write the good definition. But even in Lean, it's very easy to prove it. So we are proving an implication. So first of all, let's suppose our assumption. So we suppose S equal to T. Okay? We need to write, we need to prove that my type equal ST. But now we can use statics as we saw yesterday. So we can rewrite H. Now we can prove my type equal TT. No, because S is equal to T, so he rewrote T instead of S. Now, I can say, since my type is essentially a finite thing, I can say case is T, and then I will just have a list of cases to treat. So this is a tactic that, but it doesn't do anything magic. Now, you see that we are proving a proposition about an element of type my type. So we can, the induction principle says that to prove a proposition about an element of type my type, we only need to prove it in the case it's A and in the case it's B. So cases just use this principle for us in a reasonable way. We just writing cases, but essentially I can really write the same line using my type dot inductor, but it seems slightly complicated. So you see that now Lin responds pretty well. He says, now you have two goals. I can open a curly braces just to focus on the first one. So, and I have to prove that my type equal AA, but my type equal AA is true by definition. And we saw that proving true is easy. So this is called trivial. So trivial just realize that to prove true, there is nothing to do by definition of true. So true is the proposition that we can prove without doing anything. And trivial just realizes this fact and proves true. And then, we have the second case is completely analogous. We have to prove my type equal BB. My type equal BB is true, and so it's done. And we have our beautiful goal accomplished. Okay, so now we realized with some crazy effort that if S is equal to T, my type equal ST is true. And now we are ready to prove that A is different from B. Okay? So first, now, A different from B, we realize that it is an implication. So it means A equal B implies false. So let's start introducing our assumption. So now we have an assumption A equal B, and we need to prove false. Okay? But now, let's use this is a lemma, not a definition. Well, I don't know why I call it definition. So let's use the lemma we proved 2 minutes ago. So my type no confusion says that when you have two elements of type my type, in this case we are going to apply to A and B. I mean, they are the only one, but who knows? And the proof that they are equal, then my type equal as AB is true. So I'm just saying we are supposing that A is equal to B, so I can exactly say, apply the lemma we proved 2 minutes ago to these cases. So now we know that my type equal AB, that this holds. My type equal AB. No, you see, this is literally what we proved 5 minutes ago. But what is my type equal AB? But we can have a look. My type equal AB is false. Is false. So, and I have to prove false. So I can just say, you see that now here I introduced a new tactic, so that you didn't see yesterday. I introduce a new assumption. I say, have H, this new assumption, and now I can say exact H. Of course, I can just save one line if I want, and I can say directly exact. Okay. Because this is my type equal AB, that by definition is false. Okay, so now we have produced our beautiful type with two elements, with quite a lot of effort. No, but you see, the point is that we didn't, so the interesting part of I think that the interesting part of this proof is the following. First of all, that we didn't suppose that the two elements were different. There is no axiom saying that the two elements are different. The only axiom is that to prove something about this set, we have to prove it for the two cases, and to produce a function defined on this set, we have to say where the first element goes and where the second element goes. These two statements implies that the two elements must be different. Because the moral idea is the following. If the two elements, you see, the fact that to produce a function, you have to say, not only you have, but you can just say where the first element goes and where the second element goes. It also say that you are free to choose the two elements. So the image of you are free to choose the image of the first one and the image of the second one. So the two elements cannot be the same, because the axiom says that you are free to choose the images. And under the hood, of course, it looks like a circular argument, because yes, this is not circular if now you have another codomain with two elements, but maybe there is just one thing in the universe. And it's not circular for an extremely subtle reasons that we define not equal to be equal implies false. If we are living in a universe where essentially what we are going to say is that if you are living in a universe where there is only one thing, then true is equal to false, and you can prove anything and it's okay. I mean, the thing is completely compatible. It's just not interesting. But so there is this subtlety about the definition of not equal, but it doesn't matter. But okay, now we are ready to prove that 0 is different from 1, and this will be easy, because now we will just produce a function that sends 0 to A, that sends the successor of anything to B. Now we know that A is different from B, and so 0 cannot be equal to 1, because if 0 is equal to 1, then f of 0 is equal to f of 1, and we are done. So first of all, let's build the function. So the codomain of the function will be my type. So I have to specify, first of all, where I send 0, and I send it to A. Then I say, let's take n. Let's take S, that is the image of n. Where I send the successor of n, well, I don't even need to use S. I send it to B. So 0 is sent to A, and the successor of anything is sent to B. Okay? So now, how can we prove that f of 0 is equal to A? There is nothing to do. This is true by definition. And the tactic to tell Lin prove this by definition is called raffle. We will see it in 2 minutes in the natural number game. That is the first tactic you should learn about, but I forgot yesterday. So it just means this is true by definition. So f of 0 is equal to A. Similarly, f of 1 is equal to B. It's again by raffle. And now we can prove that 0 is different from 1. So let's start by introducing our assumption. So we have that 0 is equal to 1. We need to prove false. And we know that we have this lemma A not equal B that says that A is different from B. So the lemma A not equal B is the implication A equal B implies false. Now you see that I want to prove false. Then I can use this lemma to reduce my proof to A equal B. I can apply this lemma. This is another tactic. So you see, here the goal is false. This lemma is an implication whose conclusion is false. The apply tactic says if you have a lemma whose conclusion is the conclusion you want to prove, well, you can just prove the assumption of the lemma. No, because this lemma is A equal B implies false. So to prove false, I can just prove A equal B and apply this lemma is the tactic that does it. So now you see that the goal now is A equal B. And now the proof is done because I can rewrite F0. No, sorry, the other direction. Oop. So F0 is the lemma that says that F0 is equal to A. Okay? I can also rewrite F1. So now the goal is that f of 0 is equal to f of 1. But I have the assumption H, so I can rewrite H. And after rewriting H, the goal will become f of 1 is equal to f of 1. And Lin is smart enough to realize that this is true. And you see that he says goal accomplished. Okay? So now we have proved, really from the axioms, that 0 is different from 1. So let me just underline that we have at least learned something interesting. We have learned what negation is. And we also had learned about this new tactic apply, and also this little tactic raffle. Of course, this proof looks like ridiculously complicated for some trivial stuff, but these stuff that are very close to the axioms are not, are a little bit subtle, so it's better to be sure than to be proven wrong later. But still, in a similar way, you can prove that the successor function is injective. Indeed, in practice, a similar strategy proves that anytime you define a new thing using these constructors, all the combination of, all the constructs are injective essentially. There is a proof, a theorem automatically generated by Lin, but not as an axiom, as a proved theorem that says this. It's called no confusion. This is why I call it no confusion. So this theorem is automatically produced by Lin, to be honest. But I want to show you the proof. Okay, so to finish my lecture of today, the last 5 minutes, I'm gonna start playing the natural number game. So the natural number game is about the MyNat type. It is defined exactly as I show you. Well, I suggest you to, if you want to play it before next week, of course you are free to do it. Just be sure to read the description. It's not that long, you see. And really try to do the proof in order. So you see that now every word introduced you for a new tactic. And the interesting part is that you can see here what you already have. So for example, here he says you already have the tactic raffle, and it gives you an explanation of what the tactic raffle does. I'm not going to read all of this, but essentially it says that the raffle tactics prove that two things that are equal are equal. So for example, here is a slightly even more stupid version of Lin of what you saw. So for example, sometimes you see that in here, this last goal was closed automatically. After I rewrite H, the goal will become f of 1 is equal to f of 1. And Lin was smart enough to realize that this is true. In this version, it's even more stupid. So sometimes you have to close it by raffle. So you have to. So Kevin, the author of the game, try to make the Lin as stupid as possible to really explain you what you have to do. But you see that. So you have the goal state here. So you have 3 natural numbers, and you have to prove that x times y plus z is equal to x times y plus z. So you see that there is literally nothing to prove. So it's raffle, and you should see proof complete. So it's goal accomplished, and then you can do the next level.
So can you repeat the first level? I'm trying here to play this game, but I'm totally confused with this.
Because you didn't listen to me.
I listened to you. I need to check something outside.
Okay, so you see, okay, even bigger. So here you see that you have 3 natural numbers, x, y, and z. And this fancy symbol here is what the goal is, what you have to prove. So you have to prove that x times y plus z is equal to x times y plus z. So you see that the left-hand side is literally the same thing as the right-hand side.
Is that I'm confused? Yeah.
I'm asking you to prove that 2 is equal to 2. It's easy, no?
But I can put ring. Or no?
Yes. I don't know if maybe he has the. No, I guess that.
Oh,
no, he was smart enough. No, because Lin doesn't know that MyNat is a ring at this moment.
Oh, okay.
No, don't cheat. Only use. No, please don't cheat using all what I showed you yesterday. Use only the results that are shown here. No.
Okay.
I think that the author really paid attention to make it impossible to cheat using some power tactic, but maybe sometimes it's possible. Don't try to cheat. So here the point is to learn the raffle tactic that says that something is equal to itself. You see, this is obvious, but it's strange, no? Because if a student says to me in a lecture, yes, this is obvious, my standard reaction is, yes, if it's obvious, please prove it. And usually the student says, maybe it's not so obvious. But if you say to a professor, okay, 2 is equal to 2 is obvious, please prove it, he doesn't know what to do, no? But here, so there is something to prove. In mathematics, there is always, is it an axiom? There are only 2 possibilities. It can be an axiom or it must be proved. And so, okay, maybe it is an axiom, but maybe not. We don't know. So the point is it's not an axiom. It's a consequence of the definition of equality. Let me show you just for fun the definition of equality. So here is the definition of equality. And you see this very beautiful line is the definition of equality. And I'm not going to comment it, but you see that there is a definition.
Let me ask you, is this an issue of, say, Lean, or is it an issue of type theory or whatever, the mathematics?
Yeah, no, I wouldn't say an issue. I would say that is a quality of type theory. It's related to Lean. I mean, it's not about Lean, it's type theory. I mean, the point is that there are two notion of equality, even three maybe. But one that is really embedded somehow as an axiom, that it means that you typed the literal same thing, and with some rules. But so, and that says that these two things are equal because you literally use the same, you wrote the same thing. But then there is a definition, I mean, of what you can prove that, I mean, that of what be able to prove that two things are equal mean. But in any case, this is, so let's forget this very strange thing. Let's just say that two things, the fact that two things are equal, I mean, that something is equal to itself, it's trivial.
Just one more question. So I put ref without comma.
Yeah, put the comma. There,
okay.
I think it even says it. As I said,
it's written.
If I said, and don't forget the comma.
Oh, yeah, I didn't read that.
So please read the documentation. Okay, let's go to the next level.
More questions, maybe?
No, let me, so this is the rewrite tactic. We already knew it, but you see that what I mean is that now, here, you also have the rewrite tactic. So you can use it. So let's just do this one. So we have xy to natural numbers. We suppose that y is equal to x plus 7. And we need to prove that 2 times y is equal to 2 times x plus 7. So we just have to rewrite, what's the name? H. So now, after rewriting h, the goal becomes something is equal to itself. So usually, in what I showed you 5 minutes ago, Lean was able to close it by itself. But now, here, we have to say it explicitly. We have to say ref. So you see that this menu on the left, it's really useful because it's a list of tactics that will get longer and longer, and also a list of theorem statements that you have proved that you can reuse. Now it's empty because you didn't prove anything reasonable. In the tutorial level, in the tutorial world, there are no interesting results, I guess.
Want to ask something?
And the first line, what is h? I forget it. And the proof.
So you see, we are supposing that y is equal to x plus 7. So we are proving the following lemma. If x and y are natural numbers and y is equal to x plus 7, then 2y is equal to 2 times x plus 7. Why this is true? Because we are supposing that y is equal to x plus 7. So if we go at the goals at the beginning, so you see that we have 2 natural numbers, we have our assumption, and then we have the goal. And you see that here it's what it is shown here. We have 2 natural numbers, we have an assumption that it's called h, and we have the goal. So the first thing we do is to rewrite h. So h, we replace y by x plus 7 everywhere in the goal. So now, after rewrite h, the goal becomes 2 times x plus 7 equal to 2 times x plus 7. Now this is easy. You can just say ref. So last level I want to show you is, I suppose, no. Okay. I repeat. I really encourage you to read the description. I'm not doing it because I guess I'm able to prove it without reading it. But so now we have 2 natural numbers a and b. We suppose that the successor of a is equal to b. Now this is just to introduce the successor, but you are already expert about the successor. So why the successor of A is equal to the successor of B? Well, the successor of A is equal to B, so we can just rewrite H.
Rewrite H.
Now yes, but Daniel, the point is that you should try to do it by yourself, not like Daniel is doing, copying my proof. So
don't forget the comma, please.
Yeah. And now it's complete by raffle. So let me just, I guess. Okay. So this is your first theorem. Okay. Okay. So let me finish by this one. So here now we have to have a look at least at the definition of addition.
Oh, let's see.
So the definition is by recursion on the second variable. So it's what I showed you before. So here he introduced also the nice symbol plus, that is nice. So A plus 0 is equal to A by definition. Because so we are building a function that take a natural number n and say what A plus n is. This function is defined in the following way. If n is 0, then the result is A. So, and you see that you now have a nice theorem, add 0. And you can also, maybe in the next level you will see it here. What is the proof of add 0? The proof of add 0 is raffle, because this is true by definition. We defined the addition in that way. Now, now we also have the theorem add such that say that the A plus the successor of D is the successor of A plus D. This is the definition of addition. Again, to define addition, we have to say what adding 0 means, and it means we don't do anything, and what adding the successor of D means, and this means taking the successor of adding D. So, for example, here now we have A plus the successor of 0 equal to the successor of A. Why I don't see the theorem here? I guess I can say rewrite add such, I guess. Yes. I don't understand why I'm not saying. Yeah, sorry. You see, I'm saying the theorem. So I'm seeing the theorem. So now we have two theorems, add 0 and add such. So add such says that A plus the successor of B is the successor of A plus B. So I rewrite this theorem. You see that I didn't even specify the variables, but I can. I say A0, it should work. Yes. So now the goal is the successor of A plus 0 is equal to the successor of A. What can I do? I can now use the theorem add 0 that says that A plus 0 is equal to A. So I can rewrite add 0 H, A, sorry. Now, the goal is the successor of A is equal to the successor of A. And this should be closed by raffle. Yes. Of course, so I think all of this is explained in the comments, but you are not obliged to write the variables. Why it's not necessary? Because you see that there is only one way to apply the theorem add such here, with A and 0. So if there are more than then, you have to specify the variables. You can maybe even specify just one variable instead of two. But, okay, you can probably save some lines using the brackets, but it's not, I don't know if it disabilitated it. No, okay. And even if you want to save even one more line, you can just say raffle, and I guess it works. Yes. Because raffle is smarter than you can think. There is nothing to prove. So raffle unfolds all the definitions involved. So it unfolds the definition of addition. So he realizes automatically that these two theorems are true by definition. So raffle use them automatically because. But you will see that, I mean, I'm stopping here, but in the next level, there is something you have to prove by induction, and this will be not closed by raffle. But try to rewrite everything at the beginning. Yes?
I have a question. Sometimes it's useful. Oh, sorry. Yeah. Sometimes it's useful to not replace A plus 0 by A, but replace A by A plus 0, right? I mean.
Yeah, you can write in the you can. you can, for example, you can do something like that. So this is a wrong move, but you can do it. Add 0A, sorry. So you see that now he replaced A by A plus 0, because I said I added this arrow. This arrow is typed using \L.
Okay.
This is, of course, in this case, is a wrong move because we are. But yes, of course, if you want to use if you want to rewrite in the opposite direction, there is. But all of this is written in.
If I remember correctly, yesterday there was a way to apply it just to the second appearance of A, like adding a 1 somewhere.
Yeah, I guess that it disabilitated it in the natural number game because it's never necessary here. But yes, in the full thing, you can if your A appears twice and you want just to rewrite one of the A, you can do it. Using nth rewrite. Yeah, it's another command. I think it doesn't work here. I don't even remember the syntax, but yeah, no, but I'm pretty sure it is disabilitated.
Okay.
But because you want to keep things as simple as possible, all these variations are of course possible. Okay, so let me stress the important thing. The important thing is this menu on the left, where you have the tactics you know. So for now you know the raffle tactic and the rewrite tactics, and the theorem you can use. And so you see that if you go to the next level, and then I'm gonna really stop. I'm not doing the next level. Sorry, the level is finished. So the word is finished. We need to go to addition word. So you see that here now you have a new tactic, induction, that it is described here. And here the first thing to prove is that 0 plus n is equal to n. And you see that this is not true by definition, because addition is defined by recursion on the second variable. So here, if I say raffle, it's not going to work. Yeah, you see there is an error. Okay, so let me stop here. But if you want play, you can of course play. Just look for natural number game on Google or whatever. This is what I propose you to do together next week. So you will be with your computer, and you can just try to do some random level of. I mean, it's better to do it to following the order. So the idea is that you play the game, and I will be there to answer questions or to help if you get stuck or whatever. But if you want to start playing by yourself, you are free to do it. We will find something else to do if you already have done this, all of this game. And last sentence. I know that this looks stupid, but I think that since it appeared, all the people I know that now works in Lean, including myself, we all started with this. So I literally remember myself spending a couple of hours playing with the games. So it's really the most common entry point to Lean. So I hope you will have fun with this game.